Number 342 Oceanography September 2011 43 Introduction. Like most Arctic phenomena, the geomagnetic fade in this region is both poorly understood and critically important to the global system. Historical observations document dramatic behavior. For example, the North Magnetic Pole NMP. The location where inclination is 90 has migrated more than 1,700 km over the last century, e.g. Phaelson and Mandea. 2007, placed in the context of the present decline in intensity of the dipole failed Gubbins E. Fail 2006. Such behavior could foretell an impending reversal or excursion, e.g. Faye DeSantis E.T. Fail. 2007, because historical records are short Faye 400 Faye years. Paleomagnetic studies are needed to put the Arctic geomagnetic field into a proper temporal context. Over the last decade, paleomagnetists have begun exploring whether Arctic sediments might provide a high-resolution archive of past geomagnetic behavior. Such data can provide fundamental geophysical observations on Earth's core and the geodynamo, while also possibly providing a critically needed high-resolution stratigraphic dating tool for paleoceanographic and paleoclimate studies. Understanding ongoing geomagnetic change and NMP movement has been hindered by limitations of both historical and paleogeomagnetic data. Historical observation-based reconstructions Jackson E.T. Fail. 2000 augment the few direct observations of NMP location figure Faye 1, but only extend back to 1590 Fayad, revealing no motion analogous to the ongoing NMP migration. Based on these model reconstructions, the NMP over this time interval underwent limited motion restricted to a small region of the Arctic centered over the Canadian Arctic archipelago figure Faye 1. Compared to the historical geomagnetic record, paleomagnetic records provide additional information on the past, possibly including NMP migration over a larger area. Unfortunately, paleomagnetic records from the polar regions are rare due to the logistical difficulties of obtaining them. Records with the temporal resolution and chronological accuracy required to document centennial or shorter prehistoric geomagnetic change, necessary to provide context for ongoing polar failed changes, are exceedingly rare and just beginning to emerge. IS paper presents an overview of Arctic geomagnetism and paleomagnetism and describes recent efforts to move our understanding forward by looking at high-resolution Holocene records from the low and high Arctic. As highlighted here, paleomagnetic records from the high Arctic may be key to understanding current dramatic geomagnetic changes, as well as the unique nature of the Arctic geomagnetic fade. Arctic geomagnetism, historical observations, and geodynamo theory attest to the unique properties of the geomagnetic field of the North Polar region, e.g. Faye Bloxham E.T. Fail. 1989, Haynes and Newitt, 1997, Olson and Orno, 1999, Jackson E.T. Fail, 2000, Hulot E.T. Fail, 2002, Newitt E.T. Fail, 2002, Chuliot E.T. Fail, 2010 AB. Numerical dynamo models which explain the origin of the geomagnetic field and its secular variation by convection in the electri. Kali conducting Faye UID in the outer core e.g. Faye-Glatzmeyer and Roberts, 1995, predict that both outer core convection and the magnetic field generated could be substantially different at high polar latitudes. According to dynamo theory e.g., Fakenau and Roberts 2003, Earth's solid inner core affects the pattern of convection within the liquid outer core, which in turn affects the geomagnetic fade. Faye High Arctic is located within the surface expression of the tangent cylinder. Faye tangent cylinder, described by a latitudinal circle at Faye 69.5 north and south, figure Faye 2, is defined as the region in the outer core where Earth's magnetic field is generated, in which a theoretical cylinder tangent to the solid inner core and parallel to the axis of the HIGH. Arctic may be key to understanding Faye current dramatic geomagnetic changes, as well as the unique nature of the Arctic geomagnetic field. Guillaume Saint-Kunja UKR QC. Ka is professor in Canada Research Chair in Marine Geology, Institut des Sciences de la Mer de Rimouski, Izmir, and Geotop. Université du Québec. A Rimouski, QC Canada. Joseph S. Stoner is Associate Professor, College of Oceanic and Atmospheric Sciences, Oregon State University, Corvallis, Oregon, USA.